Okay, so now we have mass, linear momentum, angular momentum. What's left? Energy. Right. All right. So in words, the conservation of energy is that, the time, rate of change of energy in a body, right, is equal to the mechanical work plus heat generated plus conduction plus radiation. So now we just have to write down what those terms are, right? Well, so the internal energy, or the time rate of change of energy in the body, is equal to the kinetic plus the internal energy, right? So the kinetic energy is 1/2 dm v dot v, which is equal to 1/2 rho v dot v dv, right? The internal energy, we're just going to give it, the internal energy here is just going to be U. We're not going to specify necessarily where it comes from. It could be mechanical work stored, like strain energy or something, but in this case we won't be that. We'll leave it more general, such that we just have some internal energy times dm, which is rho dv, right? And so the sum of these two is the work, and the time rate of change of that is the power, right, in the body. And so that's d dt sum, which is the work, 1/2 rho v dot v plus rho u dv, which is equal to, through the Reynolds transport theorem, okay? And so the mechanical work, so this is the left-hand side. Or power, rather, power. Mechanical power comes from the same two sources. I didn't redraw our thing, but it's the same, right? It comes from body forces and surface tractions, okay? And so from body forces, we have rho b v dv. So surface forces, we have rho, I'm sorry, not rho, just T V ds. Using Cauchy equation, it's sigma j I nj vi ds. And then using the divergence theorem is xj sigma j I vi dv. Right. I'm going to manipulate this a little further. If we use the product rule here, we'll have sigma j I j vi plus sigma ji partial vi partial xj dv. If you remember, this is called the velocity gradient, Lij. All right, so that's our mechanical work. Then we have heat conduction. And just by convention, we're going to say that it's, the heat conduction vector is outward pointing, so that's defined as negative. ds. Using divergence theorem here to convert to a volume integral. And finally, radiation term. This is generally not important unless you do nuclear power. Would be something like this. So where this is R is the heat generated per unit mass. Okay? So we're almost done. Put it all together. And again, I'm not going to change anything. I'm just going to rewrite it. And you get, just going to move some terms around. You get this. What's this guy? It's the equilibrium equation, conservation of momentum, right? So that's equal to 0. So, and then, for arbitrary dv, then you'd have rho du dt is equal to sigma transpose L minus divergence of Q plus rho R. And then just one last, L, if you remember, we can decompose L into a symmetric part plus a skew symmetric part. And so if you're taking this inner product and if sigma is symmetric, then, by definition, this is symmetric and this is skew symmetric or anti-symmetric. So therefore, sigma inner product W is equal to 0. Any symmetric tensor inner product and an anti-symmetric tensor is 0. So that just leaves D, right? So the final form will be d du dt, since sigma is symmetric. All right. So energy. And so just to summarize, and this is the last thing we'll do today, energy linear momentum angular momentum And then we had multiple ways to write mass, right? All right, there's our conservation equations. And later on in the course, when we compute solutions, these are the equations we're going to solve. Now, I'll say right now, we won't do anything with energy. Although, it's just more code. It's not any more difficult. And then, we're going to use simplified. We're going to simplify momentum and mass a little bit to make it a little bit easier. But when you solve, when you use a commercial code that's fully coupled with multiphysics, like say COMSOL, that's what it's solving. All of those equations. Yes, sir.
Standard conservation of mass is supposed to be the determinant of F equals rho over rho naught.
Yeah, sorry. All right. Any questions?